So what I have up on Moodle is I have a number of different prompts to hypotheses test. And so pull that up, and what I wanted to do is I wanted to go through and talk through how we'd carry out the process of doing a hypothesis test. And so real quick, pause and take a second to read through this information. And what we have here, right, is we've got, this is a pretty straightforward quality control type question. And so I like thinking about hypothesis testing in a number of different steps. And so I think the first step that I usually do is just write down all the pertinent pieces of information. And again, right, not necessarily everything I give you is gonna be pertinent. So you gotta parse through all the information and think about what you do and do not need. All right, so the point of this is that you've got a quality control specialist. What are they looking for? They are looking for that the average of the thickness, let's do TH for thickness, what they want in their design, their manufacturing design, is that the average thickness is 7.5 1/100ths of an inch. 1/100ths of an inch. Sure, right? Really the 7.5 is the thing that's key to us, right? The units there are just 1/100ths of an inch. So that's what they want to see. What else? They took a random sample of 40 pieces of gum, right? So I'm going to do n equals 40 for that, right? They have a number of observations in the sample that they drew from a quality control run was 40 pieces. And in that sample, they obtained an average thickness of 7.525. What notation do I want to use for that? That's an x bar, not a mu, right? An x bar is 7.525 1/100ths of an inch. So again, right, conceptually, what's going on? What they want is for the average thickness of their entire population to be 7.5. So what they do is they draw this sample of 40 draws from their manufacturing process, and that sample had an average that was a little bit elevated, right? Is that number so high that it convinces them something's gone wrong, right? The other piece of information that they drew from the sample was there is a standard deviation of 0.06. Now think about, should I be using a sigma or an S for this, right? This is the sample standard deviation of 0.06. Do they know what the population standard deviation is? Nope. Instead, they use a sample. So that's going to have an implication for the way that we carry out some of these next few steps. What is the conclusion about the average thickness if they set their significance level? Remember, that's your alpha 0.05. So I think we've got all the pertinent information that we actually need to the left. And so the first thing we need to do is we need to write out the null and alternative hypothesis, right? So again, if you recall, the null and the alternative hypothesis need to be complements. It's got to be a mutually exclusive, so there's no overlap, and it's got to completely exhaust all possibilities, right? And what we do is the thing that we put in our alternative is the claim we're wanting to investigate. And really, that's what we put the burden of proof on the data to convince us of. That's what needs to go in the alternative. So these are going to be statements about the average thickness. Remember, for the null and alternative, we're not talking about a sample value, but we're talking about the population value. So I'm going to do the average thickness, and think for a second, right? So what they want is the average thickness to be 7.5. Think about what you want, what do you want to put in the alternative? Do you want to be that the average design is equal to 7.5, or should the alternative be that it's not equal to 7.5, right? Again, think about what should the alternative be, what should the null be, and think about what that means about where we're placing the burden of proof of the data. Okay, this is the right configuration, right? Think about what this quality control specialist is going to naturally believe until the data convinces them otherwise, right? That's what goes in the null hypothesis. This quality control specialist is going to approach the process believing that the machines are producing an average thickness of 7.5. And they are only going to think that the machines are malfunctioning and not doing that if the data convinces them that the average is not 7.5. Right? So again, think about what are they bringing to the table? What expectations and beliefs are they bringing to the table? Their default perspective is that these machines are working and they need the data to convince them that they're not. Think about for a second what this would look like if we switched the roles of the null and the alternative hypothesis. If I switch this, right, think about a quality control specialist who walked into a building and believed that everything was malfunctioning and needed the machines to tell him that they were working correct, right? Think about how much more stressful that would be, right? And sometimes that might be the right approach to take, but this, right, this is the correct one for this iteration of it, right? That it's natural to think that your machines are working correctly until you've got some evidence to convince you that they are not working correctly. Okay, so we've got two other things that we want to point out as we're talking about the null and alternative hypothesis. Again, is it clear the claim that is being investigated, right? What they are investigating is our machines not producing a thickness of 7.5, right? So think about what would a type 1 error look like? What would a type 2 error look like? Can you put it into words? What would a type 1 error look like for this null and alternative? What would a type 2 error look like for this null and alternative? The next step in this process is we've got to think about, for something like this, when we're investigating it with our decision rule, is the distribution of the average, which is we're focusing on what our default perspective is going to be until the data convinces us otherwise, is the distribution of that a z distribution or a t distribution? And to answer that, we got to look at the information that we're given. Are we given the population standard deviation or not? Is that unknown and we have to use a sample as our best guess, right? In this information, we are given from our sample that the sample standard deviation was 0.06. We don't know what the population is, right? And so that's a little bit of uncertainty. And so I'm going to make a little notation here that we're using a t distribution. And I think it's helpful to draw out the t distribution. It's a t distribution. Sure, it looks a lot like a normal distribution, but it's a little bit fatter in the tails if you look closely, right? This is a t distribution. Again, a t distribution is also its center. So what's the average of the average distribution of thickness? The average distribution of the thickness is distributed around 7.5 with a standard deviation of 6. We're going to normalize it with the formula that we had earlier. So our normalized t distribution 0 and follows the pattern of that we saw earlier, right? My next question is this a one or a two-tailed test, right? So this is a two-tailed test. When I look in my alternative, it's not equal, and so it is, I want to shade in my two different sides to that, right? And again, though I'm shading in two things because I've got this not equal. Step back and think for it. In words, what are we saying? This quality control specialist is looking for the average thickness to be 7.5 inches, or 1/100th of an inch, right? It could be out of control if it was either above 7.5 or below 7.5, right? So either one of those cases, it could be out of control. And notice, they're not looking for evidence to convince us that it is more than 7.5 but it's more or less than 7.5. So here we go. It's a two-tailed t-test that we're carrying out right now. The other piece of information that I want to add to this t-story is related to my level of significance. Remember, my level of significance, my alpha, is my 0.05. It's the probability of me committing a type 1 error. My alpha value is the probability that I want to put in these shaded in regions. When I have a two-tailed test, I take my value of alpha, of 0.05, and I divide it by 2. Because I'm splitting it between the two tails, because it could either be above or below. That's how I could commit a type 1 error. So the probability in each of those shaded in areas is 0.025. 0.025. 0.025, and as a thought experiment, right, how much probability is in the middle here? If I've got 0.025 probability to the left, 0.02 probability to the right. How much probability is in a t-distribution in the middle, right? It's got to be 0.95. And if you recall, right, that this area in the middle, that would be my do not reject region, right? If the data tells me that my t-statistic is somewhere really close to 0, then it's evidence that I should not be rejecting this null hypothesis. It's only when my t-statistic gives me a number that's either dramatically less or dramatically higher than my t-value, than my what's consistent with my null hypothesis, that I would reject my null hypothesis. So I can add the word reject my null hypothesis right here, right? I'm rejecting my null hypothesis. The other thing that I think I'd like to add to this is we've got a t-distribution. So what are these critical values right here that separate the reject and the do not reject regions? Again, this is a symmetric distribution, and when we calculate our t-statistic, it normalizes this the average in the null hypothesis around 0, so that these two values are the same magnitude. One's negative, one's positive. Okay, so what else do we need to know? We need to know the probability to the left of that point, and we also need to know the number of observations that we have, because that's related to the degrees of freedom with a t-distribution. If you recall, right, what we need to find out is what's the value of a t-distribution that has 0.025 probability to the left of this point, where the degrees of freedom, which is equal to n minus 1, is 39, right? In order to carry that out in Excel, we can bring up Excel, and I've got equals. And again, if I was doing a z distribution, I'd want to do the norm, right? But instead, I'm doing a t distribution. And I can bring up my t dot inverse. Oops. Let's try this again. Bring up my t dot inverse, and I've got two parameters in Excel that this formula is looking for, right? Number one, it's asking for the probability. The way that Excel is built, again, to remind you, is when I enter a probability into t dot inverse formula, it's telling me the value of t that has that much probability to the left of that point. How much probability do I want to the left of that point? For this first value, I want 0.025 probability to the left of that point. So I enter my 0.025 probability and then comma, and it brings up degrees of freedom, right? Because each of the t-distributions looks a little bit different based on the number of degrees of freedom. As the number of degrees of freedom increases, it gets asymptotically close to a normal distribution. I've got 39 degrees of freedom, n minus 1, right? Negative 2.02. And again, if this were a normal distribution, we can do norm.s.inverse. If this were a normal distribution instead of a t-distribution, and I wanted to do the 0.025, it's one of the familiar ones you might remember, negative 1.96, right? The t-distribution is a little bit further out because there's a little bit higher probability in the tails, and so your t critical value is going to be a little bit further to the left, right? But that was just as a point of comparison. What we want to do is we want to do the t-value negative 2.02. So I go back to my picture, and I can insert to this that this critical value right here is a t-value of negative 2.02. So if I have a t-value that's less than 2.02, then I'm going to be in this rejection region. And the data is convincing me that I should reject my null hypothesis. Alternatively, right, I know, because it's symmetric around 0, that this value of that defines the right-hand side reject null hypothesis from the do not reject area, it's got to be the symmetric one. So it's got to be 2.02. But if I go back to Excel, I just want to think about how I would find that value in Excel. Remember, my t dot inverse, right, is asking for the probability to the left. So if I want 0.025 probability to the right, how much probability is to the left? If I've got 0.025 probability to the right, that means I've got 0.975 probability to the left. So, right, 0.975 probability to the right, and again, I had 39 degrees of freedom. Oh, did I hit 38? I did hurt. There we go. Now that they should be symmetric. They should match up, right? So in essence, right, if my t-value is either less than 0.02 or greater than 0.02, then that's the level of screwing up that I'm comfortable with. Remember, my level of significance is the probability of committing a type 1 error when I look at my data and I had assumed that the null was correct. If the null was actually correct, the probability of rejecting it based on the data is what the level of significance represents, right? That's the standard that I'm adopting in terms of my quality control, how much I'm willing to take on this error. Okay, notice we haven't said anything about the data so far, right? All that we've done so far is we've structured, this is what the problem's going to look like. This is how we would carry out the decision-making process. Now, let's go ahead and actually look at the data, right? What do we actually know from the data? We need our test statistic. All right, back here, we've got the test statistic, and again, we don't know what the standard deviation is in our population, so instead, we're going to use our sample estimate of our standard deviation. So that means this is the configuration of our t statistic. We're going to look at the average of our sample minus mu naught. That represents the average that's in our null hypothesis, right? And then we're going to divide it by the estimated sample standard deviation divided by the square root of the number of observations that we had. Do we have all this information? Let's go back to this whole thing and write this out, right? Repetition is a good way to learn things, right? And so this is our observed average from our sample minus the hypothesized average in the null divided by the estimated sample standard deviation divided by the square root the number of observations in our sample, right? And again, that's because according to the central limit theorem, it's a normal distribution, and the variability changes in a predictable way based on the number of observations in a sample, right? If you recall back from when we first talked through that central limit theorem, as we increase the number of draws from a random observation in a sample that we calculated averages from, it changed the shape of this distribution. So the shape of this distribution is a function of how many units are produced. So pulling out the different values that we actually observed a value of 7.525. Remember, I commented at the time it was a little bit higher than what we'd expect, minus the hypothesized average from the null hypothesis, 7.5. My estimated sample standard deviation was 0.06, and we're dividing it by the average, the number of observations that we had. In this case, we had 40 observations. And so I'm going to switch over to Excel and carry this out, and hopefully I can remember all these numbers, right? So we had 7.525, we had 7.5, we had 0.06, and we had 40. So what do I have? In my numerator, I've got my observed value minus my hypothesized value in my null. So this is it's a positive 0.025. It's going to be to the right-hand side of my distribution. And then in my denominator, I take my sample standard deviation divided by the square root, I can't type today, square root of the number of observations that we had. In that case, it was 40. Right, and so that's my way that I'm normalizing my t-distribution, and I get a value of 2.63, right? So this value of 2.63, we can directly come back and think about on this chart, where would the number 2.63 be, right? 2.63. If you recall, do you recall how to interpret what the value of 2.63 is? Right, so if I look at my distribution, remember that critical value was at 2.2, and what our data said is that our data said, if the null was true, that we'd be way the heck out here. 2.63 is way out here where we're rejecting the null hypothesis. The data convinces us to reject the null hypothesis. The data convinces us that the average thickness is not 7.5. My goodness, that quality control specialist, hopefully they are screaming and doing something about this, right? Because the data was pretty convincing in telling them how that it was not where they want it to be. We mentioned that this is one main way to do it, right? So you go ahead and you calculate the t statistic, and then on this picture we can think about what that t statistic is. We said that alternatively what we can do is we can calculate from the data from the calculated t statistic, calculate what the probability of observing that level is, right? So again, if I've got a t distribution that's centered around 0 with the way that we had it earlier, we had a value all the way down here of 2 with a t value of 2.63. We can ask, right, on either side of this story, 2.63 or negative 2.63, what is the p-value? What's the probability, if the null was correct, of observing in the data a value that was this far from what we hypothesized in the null hypothesis? What's the probability of observing something thus given that the null was true? In order to do that calculation, we go back to Excel, and so far, what we've been using so far for our calculations were t dot inverse equations, right? Now we're going to go the other direction. Instead of t dot inverse, here's where we use the t dot dist, right? And when we do this, notice that there are 3 parameters here. Number 1 is the x value. That's the value that we just calculated, right? So I'm going to go ahead and select this cell of C4 because it's where this exact value of 2.635 is. Comma, degrees of freedom. You remember what that is? It's still n-1. Comma. The last one is either going to be the word true or false. And this is based on do we want Excel to give us the cumulative distribution, which is the way we've talked about this, right? The cumulative distribution would tell us the probability up to that point. Or alternatively, if we put false, it would return the marginal probability, right? Enter true. When we enter true, what this is about to give us is it will give us the probability up to the value of 2.63. So think for a second, is it going to give us a small number or a big number? It's going to give us a really big number, and we actually have to calculate how much is to the right of that. So we're going to have to make a little adjustment. When we hit enter, it gives us a very, very, very big number, not surprisingly. If we want to know how much probability is to the right of that point, 1 minus that value. My goodness, how much probability, and again, this is telling us how much probability is to the right of 2.63? Very, very little probability is to the right of that. But notice we had a two-tailed test. So really when we're doing this, it's the probability that we have data that is that far from what we hypothesized to be true in our null hypothesis, but that could happen either to the right or the left. So in that case, what I need to do is I need to take this probability and I need to double it. I need to take this probability, there we go, and double it. The correct p-value associated with this hypothesis test is 0.012. The p-value is was that what it was? I forgot. Yep, it was. P-values always between 0 and 1. 0.012. How does this p-value compare to the level of significance, to our comfort with committing a type 1 error? This p-value is smaller than the probability that we were comfortable with committing a type 1 error. What does that mean? That means we still reject the null hypothesis, right? Given what we saw in the data and given our comfort with committing a type 1 error, this is saying that the probability that we would be committing a type 1 error with observing this amount of data conditional on the null being true is only 0.012, whereas the probability we were comfortable with was 0.05. So we are clearly under that threshold that we were going to be concerned about. So we're comfortable rejecting the null hypothesis. Is there a chance that we are committing a type 1 error? Sure there is, right? If the null is true, the probability that this data was generating a false positive, it's not 0. It's a small number. It's smaller than what we said we were going to be comfortable with, but it's not 0. And that, in a nutshell, is the steps of how we'd carry out a hypothesis test. I brought up the next hypothesis, and I'm going to work through it in a much, much faster clip, but I want to make sure that my steps writing it out are clear, and go ahead and shoot me an email or ask me a question if you don't follow along. So again, pause and take a quick second to read through this information and think about what's pertinent. Right, so check what we believe to be true unless the data convinces us otherwise. 10 minutes. You take a sample of 40, and you found in your data, oh, it's actually 11 minutes. Standard deviation of 3. We don't know what the population standard deviation is. And the level of us committing a type 1 error, 0.05. Right, so those are the pertinent pieces of information. Think about for a second, what should we put as the null and alternative hypothesis? And think about where are we putting the burden of proof on the data to convince us? Are we asking the data to convince us that this administrator is correct? Or are we putting the burden of proof on our disbelief being correct? Again, the claim, my claim, that's what I'm putting the burden of proof on. I'm putting a burden of proof on this claim that it's not 10 minutes. So naturally, I'm going to believe this hospital administrator until the data convinces me otherwise. Think about whether that's a reasonable place that we should put the burden of proof of data to convince us of. Think about, do we always want to take the word of institutions, of governments, of businesses, of sellers of a product? Do we always want to believe that they're true unless the data convinces us otherwise? You might want to think about if that's the right burden of proof. And again, that's a little normative, but just think about that, because it does influence the way that we structure this. Again, think about what would a type 1 error be, what would a type 2 error be. Primarily, a type 1 error is if we look at some data and my goodness, our data tells us, oh, reject what they said, disbelieve them, when in fact they were right. That's bad. That's a type 1 error, right? So real quick, think about what type of test statistic are we looking at? What is the distribution of it? And where are the critical values? This is a t-distribution. Why? Because we do not know what the true population standard deviation is. It's a t-distribution. We've got a two-tailed test because this is not equal to, right? They claim that it's 10 minutes. I found evidence that it was more, but could it also be less, and that's the reason why they're wrong? I don't think anyone would complain about that, but, right, indeed, with the very specific way that this is written, right, it's the not equal to 10, which means two-tailed test. So I take the level of significance, which is my probability of committing a type 1 error when the null is correct, and splitting that amount equally, 0.05, split it, 0.02, 0.02. And again, so this was easy because we had the same number of observations. So the number of degrees of freedom on this t-distribution was again 39. So those critical values, negative 2.02, positive 2.02. And oh, I forgot to add my do not reject regions, right? So if this is do not reject and the other ones are the reject. So then think about, could you put together what the t-statistic is and what your conclusion would be? Rounding up. 2.11 is the calculation. Make sure all of those different pieces make sense. 2.11 on the graph. Where does 2.11 fall? Falls to the right, but not that much to the right of that critical value, right? Our conclusion is still reject the null hypothesis. We're still rejecting the null hypothesis, which means, right, they claim, the hospital administrator said, yep, 10-minute wait. We don't believe them. Right? The data tells us that we should reject their claim. But my goodness, right? Real quick, now can you pause and calculate what's the p-value associated with an observed t-statistic of 2.11 if the null was correct? The p-value following the same method we did a second ago, 0.04. So again, how does this p-value compare to our alpha? Right? It's still less than our level of significance, but think about that, so our conclusion is still reject the null hypothesis, but do you feel okay about it? Right? So again, if the null is true, we said we're comfortable with a probability of committing a type 1 error of 0.05, right? If we just had a random distribution of values, how often are we going to see 0.05, right? You can do the math. If you just do 1 over the value of the alpha, that'll tell you how many times you would have to do a random draw in order to observe randomly something that falls into these categories. It's basically 1 out of 20, right? If you did 20 random draws, one of those random draws, and again, that's if this hospital administrator was correct. If you did 20 random samples of, then, hey, 1 out of 20 of those would have a statistic where you'd be screwing up, where you'd be committing a type 1 error, right? The actual p-value, the probability of actually observing this level of a t-statistic, given that the null is true, is 0.04, right? How many times would we have to do a random sample to randomly draw something where we're screwing up and making the wrong call, right? Maybe this level of significance is set a little bit too high. And that's been one of the more recent debates in terms of some of the social sciences is, my goodness, right? 0.05, 1 out of 20, random. Oof, that's not very good. So there's a proposal to make the level of significance something closer to this, so that it's a much more stringent level of significance that we apply to data, especially with the advent of big data and so much more data out there, but putting a higher rigor on the burden of proof that we apply to our data, so that the probability of us committing a type 1 error when the null is actually correct and us falsely rejecting it is a little bit more onerous. And so that might change the amount of research that can get published as statistical findings, but it also might reduce the probability of a bunch of false positives out there in the research. But again, my focus was on the process of carrying out the hypothesis test. I know that was very quick, but email me if you have any questions about any of those pieces, but at least you've got that here for reference.